Hello and welcome. My name is Brian McAvoy.
And I'm Tim Shank. This is episode 12 of Two Cyborgs and a Microphone, brought to you by Twin Cities Plus, creating an intelligent, capable, and resilient community.
Today, we're talking about microprocessors. These have been around for years, but they've recently become a staple of tinkerers, hackers, and makers.
The only microprocessor that I've worked with is Arduino. I know you've done several Arduino projects, so you must be a fan. What's your experience?
I am a fan of Arduino. The thing that makes them special is they were the first people to really get a foothold and say, people want microprocessors. They're not expensive, and people just in their garage and tinkering want to be able to have that versatility and ability to program these. However, before Arduino, microprocessor demo boards were prohibitively expensive. So if you wanted to get into something like a Pickaxe microcontroller, you had to get a demo board, and those could be upwards of $100 and well beyond $100. Arduino said, hey, we can make them cheap.
Oh, I was going to say, and Arduinos, they're as low as $3 from China, aren't they?
Oh, if you look for microprocessor demo boards now, you can find them as low as 99 cents after shipping. They've come way down now that the microprocessor companies know that there's a huge market for this, that they'll sell more microprocessors if they're not just focused on people who are only going to ship and build 10,000 items. So if you get 10,000 people each ordering 100 of these, you've got a huge market there.
What is the actual difference between microprocessors? I mean, I know Arduino is kind of the icon in all this, but how do they vary from one type of microprocessor to another?
Well, I think first we should say what an Arduino is. An Arduino is basically a demo board. A demo board has the microcontroller right on it. It has the supporting components, in the Arduino's case, capacitors, a crystal, and it also will break out the pins so they're easy to access. Arduinos often, not always, also use a serial converter so that your computer can talk to it through USB. In fact, the very first Arduino had a serial port, a DB9 serial port. Now they're all USB. USB or Bluetooth or Wi-Fi, but generally they all have USB.
So about 50% of what you just said is like, I don't know, Spanish as far as I'm concerned. I can't understand it. When we're talking about microprocessors, you just listed off the different chips on that board. Is that correct? I mean, what I heard you say was, I heard you talk about the processor and other components. Is that right?
So a microprocessor is the core chip. This is the thing that receives programming. This is the brains.
Okay.
All the other stuff on the chip just supports the brain.
Gotcha.
And they're relatively inexpensive. If you buy one of the $25 Arduino boards, it's got a chip on there that if you just go buy that from a regular electronics vendor, it's only about $4. Now that means you have to install it onto a board and probably solder and add all the supporting components, but the actual brains of it are very inexpensive. And microcontrollers include other things like a Pickaxe. Those were kind of the competitor for Arduinos, which are a microcontroller made by Atmel.
So a Pickaxe is a brand of microcontroller.
It's either a brand or a series or a line or something, but
Gotcha.
Yeah. It's kind of like saying Arduino is a Toyota and Pickaxe is a Honda.
Let's give a broad definition of microcontroller. What is it?
A microcontroller, in the most basic conceptual thing, is the brains. It's the thing that does the thinking and the switching. So a microcontroller will have inputs and outputs.
Is there something we can say to say a microcontroller does this? I mean, we've talked about inputs and what calculations and outputs, but what is that? Is there a user-friendly definition?
Let me think on that. We can say, imagine a microcontroller is a little guy inside there who looks at the inputs, and then he flips switches on the inside depending on what you want to happen.
That's a good way to handle it. So you have this little guy, that's your microprocessor, and he's watching some stuff. He does different things depending on that stuff.
Yep, he's inside of this little processor and he's flipping switches or turning knobs.
Okay, so we've covered the basics of microcontrollers.
So now I think we need to focus on what can we do with them. We've talked about your project and my project, the distance sensors, and we use 2 digital inputs for that. I'm going to get real specific on this one just for a second. We set an input high. It asks the distance sensor to take a distance reading. We wait for an input from that distance reading. We measure that time. That time computation happens, and then we decide on what we want an output to be, whether that's a frequency or a vibrating motor to turn on or serial data to pop up on your computer.
Right. Well, that makes perfect sense, Brian. What kind of microcontrollers have you worked with?
I've worked with the Arduinos, nearly everything from Dewey Millenove up to the Leonardos. Currently, it's late 2016, so that list will change. And I've also worked with the Raspberry Pis. The Raspberry Pi are kind of a weird middle ground between a microprocessor and a microcontroller because they're a computer processor.
Oh, no, there's so much more than that, Brian. A Raspberry Pi is a full computer. I mean, it has inputs, it has DVI, it has different outputs, it uses USB. So
it's totally a computer.
Yeah, it's a computer, which does have a microprocessor in it. But that's multi-threaded, that can run different operating system. I don't think we should even get into the Raspberry Pis because that's a whole different beast.
Okay. Can I summarize it and just say it's a computer that also has I/O?
Yeah.
Let's leave it at that. What we want to focus on with the microcontrollers is just the I/O. We're not worried about how much processing power it has because these generally do not have a lot. You can get into the higher end ARM processors where you can do some pretty far out calculations, but the simplest ones, the ones that are good for biohacking and the kind of projects that we've made, which are pretty basic, they kind of struggle with the hard math. They run at 8 megahertz. They're not blazing fast speeds.
A microcontroller is kind of limited or defined by it's a single-threaded processor and a single processor, whereas things like the newer single-board computers, I think Raspberry Pi 3, those are multi-threaded processors, multi-threaded, multi-core processors in some cases.
Yeah.
And that's very different.
Yeah.
Is that accurate?
That is accurate. And to give you an idea, the newer single board computers and mobile devices have multiple cores, whereas a microprocessor, their analogy is they have multiple timers, and that's luxury items, which is nothing fancy compared to multi-core processors.
With an Arduino or any microcontroller, I have a single set of instructions that I can run. I can loop it, I can do whatever I want, but it's a single thread of instructions that I can run based on the input and use those instructions to generate an output. Is that right?
That's correct.
So now that we've talked about microcontrollers and kind of defined those, what's possible with a microcontroller? I know that's a really open-ended question, Brian.
Yeah, where to even start with that? So generally, you're going to have some kind of input. We already talked about those. You're going to have some kind of output. We've already talked about those. And this is the middle ground. This is what does all the hard work. My very first professional job, I was a industrial integrator. I worked for a company that would take industrial machines and integrate all the parts. We'd have maybe a giant block presser, and we would have all these switches that would say, okay, the block presser's full of material and the person has pressed the go button. Now I want you to start compressing this material, and once you reach a particular pressure, I want you to stop, reverse some of these processes, and spit the block out.
So the input is the amount of material, some kind of sensor or something to say that there is material to compress.
That is one of the inputs.
And the output is the calculations are when that material is present, then work these motors, then trigger these motors to compress. Is that right?
That's correct.
So that's pretty basic. Let's get a little more complex. What else can you do?
That was a pretty basic one. The big thing about integrating is you break everything down into very small parts. When you have it in very small parts, it's kind of easy to think of it as a simple project. Even though it could be doing a lot with a lot of complexity, ultimately it's ones and zeros. One of my projects that I did for that very first job was starting and stopping 50 conveyors. And ultimately, they were a lot of little programs adding up to something much bigger. So it is a hard question to answer. But that also gives way to the point that these little chips can do very, very powerful things, or at least it'll appear impressive to your friends.
Well, one of the things that I'm kind of struggling with is this multi-threaded thing. You can't do more than one thing at a time. The challenge of it is that I can't say, while you're waiting for this, do this. That's impossible in a single-threaded microprocessor.
That's a good point.
So that's one of the challenges with the microprocessors and microcontrollers too, is that there is only one thread. So while it's waiting, that is something it's doing, and it can't do anything else but wait until the next instruction comes. Mm-hmm. So that's a challenge for me when I'm used to multi-threaded stuff, computers and Raspberry Pis. I'm great at Raspberry Pis, but with the microcontroller, while it's waiting, I can't say, well, while you're waiting, do all these other things. That's the trick for me, and I guess when in the Arduino at least, but probably in all microcontrollers, the trick is to use a clock at that point, because then you're not waiting for an event, you're doing things on a schedule.
That's just a matter of how you program it. You bring up a good point about the limitations of microcontrollers. They can only do one thing at a time. They work by doing it very quickly. You can take a distance reading, turn on a motor, and keep the motor running while it's sensing something that's, maybe 2 inches away. Take another reading and change the motor based on the output. It happens so fast you can't really notice that there's a difference. It takes a computer to notice
I understand
those small differences.
So let's give some examples of what our listeners might choose to do with a microcontroller. And it doesn't have to be Cyborg related, but it should be. Probably we should lean towards that.
Okay. So I'll talk about one that has a rather complex input and a very simple output. It's basically the north sense that Cyborg Nest did. The data coming into a microcontroller is going to be from an IMU, which is an inertial movement unit. I think that's correct. And that basically tells what the position of this unit is. It'll say, I'm facing north at a 20-degree tilt with 40-degree roll. It senses all these acceleration, gyroscope, magnetoscope, and it knows its relation to you or the ground or whatever you want to sense. Think of a Wii remote. That's an IMU, or an example of an IMU. You could say, okay, I want to read all this data, and when I'm upright, facing north, and moving, I want you to turn on a vibrating motor. That would be enough to emulate north sense.
So the input is positional, and from that, the calculation in the microprocessor.
And there's a lot.
Is
IMUs are not simple devices.
So it senses that and says, when I'm facing north and in motion, then send a signal, a current, to these outputs, which you then hook up a vibration or a vibrator.
Sure.
Is that right?
Now, we could flip it around and say, have a very simple input and a very complex output, because this is still talking about what the brains of it are doing. You could simply have a single button, and that button could trigger your microprocessor to connect to a Wi-Fi chip, connect to your router, and send an email saying somebody has pressed this button at this date and time. And that would be a much more complex output.
Gotcha. Okay. Let's list your projects. I know there's a ton of them.
How about I just tell you the one I'm working on right now?
Okay, fair enough.
It's a theremin. It's not a true theremin. But what it does is it uses a couple distance sensors, because these are cheap little devices. They're about $1. And it will turn giant gears to a particular location. And the processor, all that's doing the entire time is reading a distance and turning a motor, and it's reading that motor position based on a potentiometer. And it's basically acting like a servo, and it is a servo circuit. I think the code for that was 125 lines. Very, very short.
Wow. Wow. Okay. So that has applications in robotics. I mean, the same concept has applications in robotics and all sorts of other fields.
Oh, definitely. Being able to sense your environment the way this does and turn on and off motors based on that input, that's robotics.
Is Arduino your favorite?
It's the one I'm familiar with. There is a huge community, and this is what I really love about Arduinos and what gets me excited is if I see a cool sensor on eBay for 99 cents or read about a cool project, it's very likely that I'll be able to go out, find information on that, and very often people have already written something for it for Arduino. So I can take what they've done, understand their code because I've worked with it, and integrate that into my own project. And sometimes it's as easy as copying and pasting. People who have very little experience programming or even none can pick up an Arduino, program in the included sketches, they're called sketches, and get something to work without any changes to the program. There are tons of examples that Arduino gives you for free. There are tons of examples in the community. And just by downloading somebody else's code and just tweaking it a little to see the differences, you can learn a whole lot. And that's how I learned on Arduino, is just fiddling with stuff, tinkering.
And programming I think I've been doing programming for a long time. It's an intimidating concept to people who haven't tried it, but
I agree.
Really the only prerequisite to programming is common sense. If you can understand cause and effect and timelines, it's programming something is not difficult. Is there any more to say?
There is an entire podcast series that could still be said about this, but I think for people who are maybe worried about having to get into programming for their biohacking project or just their electronics projects, I think we've said quite a lot, and hopefully enough to get some people interested.
Well, I hope so. Enough to get them started anyway. So thanks for listening. We'd like to invite our listeners to email us at 2cyborgs@TwinCitiesPlus.
Our usual thanks to Zach Dolan. He's the guy who turned us into cyborgs on paper. I'm the guy on the left. This is Brian McAvoy.
And I'm the guy on the right. This is Tim Shank. Please listen in next time where we talk about why.
And that's why we biohack, why we stick metal under our skin and insist that our phones be able to read us through our hands.
So that's kind of long in coming, actually. We probably should have hit that subject up beforehand. So I hope you'll join us. You have been listening to Two Cyborgs and a Microphone, brought to you by Twin Cities Plus, creating an intelligent, capable, and resilient community.
Like, follow, share, +1, and don't forget to subscribe on any of the popular podcast services, including Google Play Music, iTunes, and Stitcher.
Subscribing, that's really helpful, you guys. So everybody, please subscribe.
Yeah, help us move up the podcast ladder, and comment and subscribe on iTunes.